Hello, this is Dr. San Abdullah with the course Deep Reinforcement Learning. And this course consists of several critical and important topics. And one of those topics is convolutional neural networks, which is topic number 7 in that list of topics. And the subtopic is D. So the lecture is 7D. So from moderate to difficult level concepts. And this video uses the supplemental website, which is available at www.ezmcq.com/GoGet, which is a personalized learning management system. The approach adopted in this course is based upon content delivery, and the features of that content delivery are listed on your screen. And this is ahead of the traditional slides based approach. And this approach is literally used by hundreds of millions of online users throughout the world. And based upon that content delivery, we have developed the personalized learning management system. In green color is the URL of the personalized learning management system, and it consists of several features. The key 6 features are shown and demonstrated in 6 videos. The URL of those videos is shown on the screen in blue color. So, what are those features? For example, full text search in the content of all the questions and answers, and ability to support people having handicap or disability or some limitation of viewing, so they can send or set the color, size of the font, spacing, and so on. And it optimizes the limited space of the smart handheld devices in a hierarchy of the content. And then, of course, you can also track your progress so that you know what you have done and what you need to do. And there is the facility of online testing and grading and evaluation of results. And of course, this is centered around the question and answer based approach, which is engaging, which is thought provoking, which is very powerful, which is proactive also, and the details of the traditional approach. So it's the best of both worlds, and it is a blending of these two technologies and techniques. So in front of you is the list of topics which are covered in this course, and we are at topic number 7. That topic is convolutional neural networks, and the contents of this topic are on your screen now. Every question and answer is a concept. So those concepts are divided into groups. So the lecture number 7A grouping is shown in yellow color, and the next grouping in green color, and so on. So the difficulty from yellow to purple increases progressively. Now, without further ado, now we move on towards the actual lecture. So we start with deep learning section 7D of CNN, convolutional neural networks. So you may have heard about cross correlation. So it's very important aspect, and we will be covering this in this Q&A or the concept. So what happens in cross correlation is that we have an input and we have a kernel, okay, and using that input and kernel, right, we create a feature, and we create we produce an output feature map. This is the output feature map we produce. So more precisely, cross kernel correlation, right, is as you would have guessed by now, it's central to feature extraction in convolutional networks, CNNs, which is of course used in deep reinforcement learning. So the process actually begins with an input feature map. This is the input feature map, which could be a game frame, and applies a small kernel. This is the kernel, right, that slides over the input to perform element wise multiplication. So this is sliding, like slides over this 2 by 2, then this 2 by 2, and then the next, and so on. That slides over the input to perform element wise multiplication and summation. So it's not only multiplication but also summation, and it produces a feature map. So that is the feature map I am talking about, and look at the multiplications and the summations. So what it does is that it helps the model detect patterns, detect edges, and other useful information. So this is a multiplication. It's a matrix multiplication operation. So the devices which are good at these, because in games there's a lot of matrix operations, and we can see that in CNN and deep learning there are a lot of matrix operations. So you can figure out that the GPUs which were initially used for games, they have tremendous applications and use in deep learning also, as you can see here, and that is hardwired also, very fast. So now this is commonly referred as convolution, but the deep learning frameworks usually implement cross correlation, which simplifies computation, okay, and is sufficient for learning spatial features. So we are concerned more about the spatial features in space. So this operation enables the agents like agent in a reinforcement learning environment to convert high dimensional raw data into compact and structured representations, and they support better decision making and learning efficiency in a complex environment. So this is what we'll be this is kind of a gist of what we'll be covering, and here's an animation for a better understanding, right? So on the left is the image, then there's a kernel, then there's a CNN, a kernel window is moving, right, which is a 3 by 3 window, and which produces the feature space, which is the convolved feature space, right? So it's for your better understanding, and its mathematics is over here, okay? So the mathematics here, and this is the animation for your better understanding, okay? So now let's look at these uh, bullets. So input feature map. No, the input feature map is a raw spatial input like images or states, right? And it retains the structure for the kernel I've shown you to extract what localized information based upon that grid of that kernel or the matrix of that kernel, and allows the network to understand the patterns in specific regions because it's moving in a convolved manner. Then we have that kernel filter matrix. We have the kernel filter matrix, which is a learnable small matrix, okay, and that detects patterns. It interacts locally with the input. It helps capture invariant features like edges or motion for a video, and it is essential in deep reinforcement learning settings. Okay. Now, when we have done this, so we have defined the input feature map and the kernel, and then we do the cross correlation operation. So what it does, it's performs local dot products between the kernel and the input. I've shown you the kernel and the input, and it's repeated spatially to create a new feature map. Okay, and we've seen that the new feature map, I've given you the example, shown you the mathematics. The beauty is that it preserves the spatial relationship while simplifying the data. So the unnecessary details are not there, but there's also limited loss of necessary detail. And finally, we have the output feature map. So the final feature map shows where the patterns exist, right? And acts as compressed input for further analysis. What further analysis? It will help build hierarchical representation for better decision making in reinforcement tasks. So this is kind of a fine tuned for decision making in a uh, in a RL environment. Okay, reinforcement learning environment. Okay, so here are the details for your better understanding, and if you would, and here's some mathematics here also of that single input value, and here are the references. Now we move on to the next concept or Q&A. What filters to use in CNN for feature detection? Example, how to detect the edges and the blur and so on. All right. Okay. So what we'll be covering here in this concept would, these are some of the bullets, and of course I'll go into more the details of these bullets, and these are the filters. I won't be going through like in detail of all the filters, but for example, this Sobel filter, this is more popular, and here's the example of the Sobel filter, and as you can see that this is the image, and this is how it gets processed, and this is one of the filters which is used in CNNs. All right. Okay, so let's start with the some background, and then we move on to the bullets. So in CNNs, filters are used, which are called as kernels also, which are small matrices. And what is the purpose? The purpose is to detect edges and textures and patterns in images. Now, in early layers, like from starting from the input, simple filters like edge detectors, like the Sobel filters or pre-bit filters are often used for learning. What they do is they highlight the vertical, horizontal, or diagonal changes in pixel intensity. What is the purpose and how do they say? These help in identifying the object boundaries, right? Object boundaries. And then are the blur filters, such as Gaussian filters, which kind of smooth the image and reduce the unnecessary detail like noise. And what it does, it improves the robustness of subsequent feature extraction. So as we move towards the output, so we move in the deeper layers. CNNs automatically learn complex filters, right, that capture higher level features. So we're starting from the lower level features and to progress towards higher level features like shapes or corners or specific textures. Now, what happens that in traditional computer vision, filters are manually designed. So that's like feature engineering. Now, CNNs learn optimal filters during training via backpropagation when the errors are basically computed and the weights are adjusted to minimize the loss. So the type of feature detected depends upon the values that have been learned and the data itself. So what is the benefit? This layered learning of increasing abstractness of the features makes CNNs highly effective for image recognition and object detection tasks for reinforcement learning. All right. So what we'll be covering here is this example I've shown you. So what are edge detection filters? What are what are edge detection filters? Like the Sobel filters and the pre-bit filters. These filters identify the areas in an image where there is a sharp change in intensity. That is the edge, such as object boundaries or contours. So what these filters do, they highlight significant transitions, okay, which are crucial in the early scene and layers. For doing what? For locating features and defining the structure of the object. Then we have the blur detection features. Now, blur detection filters help recognize out of focus regions by analyzing the lack of sharp changes in pixel intensity. So if the images are blurred, okay, then it's not a problem because the blur detection filters uh, kind of analyze those regions and help, and the CNNs can use such filters to assess image clarity, and that haziness could be due to motion blur, so that gets detected, and that is useful in tasks like image quality analysis or video frame selection where the blurriness is kind of natural. Then are the sharpening filters like the Laplacian filters and the Gaussian filters. So the Gaussian filters apply a weighted average to surrounding pixels. The Gaussian filters apply a weighted average to surrounding pixels. What is the result? It smooths the image and reduces the noise. And they are commonly used for pre-processing to stabilize feature learning by reducing the high frequency variations. Why we want to reduce high frequency variations? Because they can distract the network from important structural patterns. We have the sharpening filters also. So what does the sharpening filters do? Laplacian filter is one of the sharpening filters. So the sharpening filters enhance the edges. That's what sharpening is. And it enhances the fine details in an image by increasing contrast at the edges. Now, how does it help CNN? It helps by better distinguish closely positioned features or textures. And what is the outcome? It can improve precision of feature localization in subsequent deeper layers. So one of those examples is the Laplacian filters. Now, Laplacian filters, what is the benefit? That they can detect regions of rapid intensity change. How it is done? By calculating the second derivative of a pixel value. So what is the outcome? That the edges and fine texture details are highlighted. And what is the purpose? They are useful for capturing subtle features that are simpler gradient based filters which might be missed. All right. And finally, we have edge enhancement filters. So what do the edge enhancement filters do? They accentuate edges and transitions, okay, in an image, obviously, without significantly affecting the surrounding region. So what is the outcome? The outcome is that the feature contrast is increased. When the feature contrast is increased, it aids CNNs in clearer segmentation, in for better object detection, especially for the inputs which have a low contrast. And then are the Schar filters. Now these are special edge detectors that help in improving the gradient estimation accuracy for the Sobel or Pivot filters. And they are especially effective in detecting the edges with minimal distortion, right? Therefore, they are useful in CNNs whenever there is a need for high quality gradient. All right. So here are the some of the not some, 6 type of filters, and then the application of one filter. And here are some details for you to read, and here are the references. Now we move to the next concept. Now we are seeing that convolution and filtering are seems to be related. So the now we would like to know and discuss with you that how convolution is closely related to filtering, and discuss it using examples. Now what we'll be covering here are these are some of the subtopics, so to say, or whatever we are going to cover. These are the bullets for it, and here is the further explanation of those bullets. And here is a real example. Okay, is a real example of the calculations of the Sobel filter which we discussed in the previous concept or Q&A. So before we proceed, a very brief overview of the background. Now, convolution in deep learning, it has its origins from the mathematical concept of filtering. And where does it comes from? Comes from signal and image processing. Now, convolution is a mathematical operation, and it combines two functions, and the result is a third one. Now, in CNNs, it consists of applying a small matrix kernel, which we already covered, to an input data such as an image. It could be video also. What is the purpose? Is to highlight important features and suppress other features which are not so important. And you know up till now that this uses a sliding window technique, and where the filter or the kernel moves across the input and performs element wise multiplication and summing results. I've shown you the mathematical formula also. So what it does is that it helps detect spatial hierarchies in the data, right? Now, traditional filtering techniques use similar approaches for edge detection, sharpening, or blurring, but here we are taking an additional step. Now, what happens is that both convolution and filtering have the same goal, which is feature extraction and identifying manual patterns in the raw data. I'm sorry, identifying meaningful patterns in the raw data. Now, filters can be designed to detect vertical edges, lines, or textures, or horizontal edges, or diagonal edges. We discussed this in a lot of detail. Now, additionally, convolutional filters enhance key signals and reduce noise also, which is of course done in classical filtering also. And basically, the purpose is to isolate frequency components or cleansing of the signals. Now, functionally, Convolution and filtering are equivalent in several ways, but there's a key difference also. The key difference is in CNNs learn their filters during training, while in traditional image processing uses hand designed filters. So, what is the benefit? The learnability gives CNNs their power in the visual tasks. So, if you look at here, you have this input image, and we have this horizontal Sobel filter. And what we do is we slide this filter across the image. Now, since both are 3 by 3, for the sake of simplicity, the filter covers the entire image, right? And then we perform that multiplication and addition also, calculate the result. So this is the input image, right? And this is the output result of Sobel filter. So where a 0 is denoted by a black pixel, and the non-zero values, which are the ones, they are denoted by white pixels. Threshold can be set also. So this is how it works. Okay. So more on this mathematical operation. Convolution is mathematically equivalent to filtering, that we have discussed, but there's a training aspect also in CNNs. Now, involving the dot products between the input and kernel values is there. As I discussed, that in CNN these filters are learned, while in traditional filtering they are fixed. Then is the sliding window. Sliding window, both filtering and convolution use a sliding window. That is the common thing. And what does this mechanism is applying the kernel over the input matrix, producing localized transformations at each step. Right? That is done, and that I've shown you also. Then is the feature extraction. Filters used in convolution extract meaningful features. Filters extract meaningful features from the data, which are similar to edge detectors or texture analyzers and in traditional image processing. So that is some level of commonality. And then is the signal enhancement. Like traditional filters that enhance useful components, CNN filters boost feature importance for classification or the detection of tasks. Some details are here. And finally, noise reduction. Noise reduction. So the convolutional layers in CNNs, like the traditional filters, help in smoothing the data and reducing irrelevant noise during the feature extraction. So this is the coverage here, and if you should be reading all those details, right? I have covered briefly the key points, and if you are interested, these are the references for further reading.